Okay, so today we'll go over continuity and a bit more on the integral test and alternating series tests. So I'm probably not going to write it all out, but for example, hopefully you all know this, right? Alternating series tests. Basically you check, A1 bigger, so your sequence is decreasing, right? And limit n goes to infinity, an is 0. And these are all positive, right? Positive, and greater than 0 for all n. Then you have some an negative 1 to the n converges. Yeah, that's pretty much alternating series tests. So, and then integral test is sort of the same thing. Your function's decreasing, non-negative, and goes to 0. Then if the integral converges, the sum converges. So I'm just gonna quickly just go straight to the questions because I feel there's not much, going on here. So, for example, 15.1a, right? So very simple, sum negative 1 to the n over n. So here, right, what is my an? My an is 1 over n, right? Because if you write it at this form, your an is 1 over n. So you just check, right? 1 over n is decreasing. So, and limit n goes to infinity, 1 over n is 0. So it's pretty clear it's decreasing, right? Because 1 over n plus 1 is less than 1 over n. So for like other cases, just check that the derivative is negative, or if it's pretty obvious, you can also just state it. Okay, so let's move to something harder. So let's go 15.2. So we need to justify whether the series converges or diverges. So some sine of, what is that? N pi over 6. Let's just start at 1. Okay, does this series converge or diverge? What do you all think? Anyone? So what is a necessary but not sufficient condition for a series to converge? In other words, if a series converges, what do you know about the terms? What? Yeah, I mean, the answer is diverge, but like, you have to say why, right? So here, what do you know about if the series converges? So if series converges, what can you tell me about this? What does this have to be? Yeah, it has to be 0, right? So, but let's write out what this sequence is. So I'm just gonna write out the first. So sine of pi over 6 to the 1, that's my first term. Sine of pi over 3 squared. Sine of pi over 2 cubed. And so on and so forth, right? But what I want you to pay attention to is this term. So when n is 3 And let's add in, you know, what other numbers? Let me think. I think 15, right? We think 15 divided by 3 is 5 pi over, yeah, 15. So you just keep adding 12. So 27, 39. What are all these terms? What is like the sine of 15 pi is so I'm just adding 2 pi, right? Because 2 pi is the same as 12 pi over 6. So that's why I'm adding multiples of 12. What is sine of pi over 2? Great. It's 1, right? This is just 1. And I don't care what this power is, because 1 to any power is 1. So pretty much my sequence, no matter how far I go, I have infinitely many 1s, right? So can my limit be 0 in this case? Yeah, I can't, right? I mean, you can use the epsilon delta definition, right? So to go to 0 means you're within epsilon. So choose epsilon to be a half. Then your sequence is within a half of 0 for large enough n, right? For n bigger than n. But no matter what capital N you choose, there's always a 1 past it, right? So it's impossible. So this diverges as not equal to 0. Yeah, everyone good so far. So let's do the next one. So this is part A. I think part B is the same thing, but with a 7 now. Okay, this is a bit different because if we try to do the same thing, what is this thing? What is this limit now? If we try to do the same approach as part A, what is, you know, this limit? So beforehand, why was it not 0 on top? In fact, you could have used the -1. You could have used 3 pi over 2 too, and said there was like infinitely many -1s. But the point here is, with the 7 on bottom, you will not get divide by 2, right? So the terms -1 and 1 is not in your sequence. But if they are not in your sequence, all the other terms of sine, I don't know what it is, but I know it's between -1 and 1, right? And what happens, you know, when you take powers of numbers between -1 and 1? What happens to it? Like, okay, like what happens to a half? They get small, good, but not only that, where do they go? Yeah, they go to 0, right? So this limit is 0. Yes, so because you only have finitely many terms because it's 2 pi periodic, and those finitely many terms, I mean, if you ignore the n, there's only the raising it to the nth power, you only have finitely many terms, and you're pretty much raising those finitely many terms to the nth power, and no matter what they are, they're between -1 and 1, so it's going to go to 0, right? So you might suspect that this converges, right? So what tests do we have that, you know, for like nth powers of things? You know, what test is there? How do I get rid of the nth power? I guess. Yeah, there's a root test, right? So let's take the nth root. And then remember, we take the lim sup of the nth root, and if it's smaller than 1, it converges, right? So let's take lim sup of the absolute value of sine to the n to the 1 over n. So the nth root of an nth power cancels, right? So this is just lim sup n goes to infinity of sine of n pi over 7. Okay, we are done because I don't know what pi sine of pi over 7 is. So there's only finitely many, right? Because we only go from sine of pi over 7 all the way to sine of, is it 14? Yeah, 14 pi over 7, right? Because the next one's the same as sine of pi over, because sine is 2 pi periodic, right? So if I add 2 pi, which is 14 pi over 7, it's going to repeat. So I only have finitely many terms. I have 14 terms, I guess, 14 terms. And the lim sup is just the maximum of them, right? The lim sup is just the biggest one, right? It's the max of the I between 1, 14 sine of I pi over 7. But like the max is less than 1, right? Because none of them is 1 or negative 1. So the lim sup is smaller than 1. So that this thing converges, yeah? So converge. Everyone good so far? Great. So let's do 15.4, I'll let you all do it. Yeah. All of them is take integral. And basically when you see log n, you use u sub. Pretty much you do u sub and then you integrate. So let's go to the theoretical ones now, right? Or maybe I'll just do one of them for you. Let's just do one of them. So 15.4 part B. So sum n equals 2 to infinity log. So again, I'm just gonna assume log n is base e. If not, then base change and pull the constant out. So here, right, it's you just integrate. And then your bounds are like these bounds. So, hopefully you all remember how to integrate from, again, it's math 2b. This is limit t 2 goes to t. And then you do a u sub, right? So let u be ln x, du is 1 over x dx. So you get limit t goes to infinity, integral of, so when x is t, u is ln t. When x is 2, u is ln 2. And then it's just u du, right? So this is, basic calculus, ln 2, ln t. So this is ln t squared over 2 minus ln 2 squared over 2 with a limit, right? So I evaluate. Okay, what is this limit? So really, I don't care about this, right? This is some number, right? It doesn't really determine converge or diverge, right? So everything's determined by where this goes. So limit t goes to infinity of ln t is what? Yeah, it's infinite, right? So so some diverges. So let me warn you one thing. The integral test. Let's say instead of infinity, I got a number 5. The integral test says because the integral converges, the sum converges, but it doesn't say like the number's the same, right? So if you integrate and you got the number 5, it doesn't mean the sum is 5. Yeah, it just means like if you got 5, it just means your integral converges, so sum converges. Your sum could possibly converge to a number other than 5. Yeah, so just be aware. Okay, let's do something different. Let's do an even number. So give an example of a divergent series sum an for which sum an squared converges. So 15.6 sum an diverges, sum an squared converges. Does anyone have an example? So they want an example of an, pretty much. Yeah, 1 over n, right? Like sum 1 over n diverges, but sum 1 over n squared converges. Yeah, of course, I'm doing 1 to infinity, right? So, okay. So this is part A. So part B, I did it for the general case, right? I did it when like for an to the p power in last discussion, not just an squared. So just look back for 15.6b. 15.6c. So I want sum an converge, sum an squared diverge. Can anyone give me one? Yes, exactly. So we're going to use alternating series. So sum -1 to the n over root n converges by alternating series. But if you square it, well, what's -1 to the n squared? That's just 1, right? Because when you raise -1 to an even power, it's always 1. And so it's just 1 over n, right? And that's diverges. Okay, is everyone good so far? If so, I'm gonna move on to continuous functions, if that's okay. So is everyone good? Okay, yeah. So I don't know why the professor skipped. I guess because it's probably not important, but she did skip a chapter. I think she skipped like she skipped like decimals of functions. But anyhow, let's move on to continuity. Yeah, because I feel that's the harder part. So the definition is, mathematically it's this, right? Limit x goes to a. F of x is f of a. And sequence-wise, it's for all sequences xn going to a, limit n goes to infinity. F of xn is f of a. So there's like a neighborhood definition and sequence definition. Now, note that this here means 3 things, right? It means f is defined at a, or yeah, near a actually, at an near a. 2, limit exists. And 3, limit is f of a. So, there's sort of 3 implications here when I write this. So let's sort of see examples of discontinuous functions that don't satisfy this. So can anyone give me an example, like here would be an example, right? If I have a function given like this, voila. Let's say this is 0, yeah? This is not continuous at 0, right? So let me just write, this is definition for f continuous at a, yeah, at the point a. So not continuous at 0. Why is that? So the limit has, here the limit doesn't exist, right? Limit x goes to 0, f of x equals does not exist, right? I mean, if this is my f. Why? Because if this is 1 and this is 2, limit x goes to 0 from the left is 1. Limit x goes to 0 from the right is 2. So this, if I call this two fails, right? I guess 2 and 3, right? But really, it's 2 because the limit doesn't even exist. So the limit cannot be f of a because the limit doesn't even exist. So is everyone clear on this? So can anyone give me or think of an example where 2 is good, 1 is good, but 3 fails? So I want limit to exist, but not be f of a. Just think of the, yeah, pretty much, right? So, maybe not move the point. You need to move more than the point, but because here I need the limit from left and right to be the same, right? So what you want to do is do something like this. And then here's your point. So here two succeeds, right? Because limit, if this is 0, right, and this, let me call this value 1, 2. Limit x goes to 0, f of x is 1, right? Because the limit from the left is 1 and limit from the right is 1, right? But this is not equal to f of 0, right? Sorry, let me write it here. Not equal to f of 0, right? Because f of 0 is 2 from what I wrote, right? So in this case, it's not the value we want, right? So continuity basically means the limit of as x goes to a, you can just evaluate it. You just plug it in, yeah. So is everyone clear on this? Can anyone give me an obvious counter to 1? It should be fairly obvious. Like, give an example of like a function not defined at a point. So yeah, like 1 over x natural log, right? Like here, like yeah, like limit f f of x equals 1 over x is not defined as 0. So not continuous at 0. Yeah, that's pretty clear. Okay, so is everyone, at least picture-wise, understanding what continuity is, or at least counterexamples to, things that are not continuous? Okay, great. So you see here, if you want to show something is continuous, you pretty much want to use the left-hand side definition, right? Because the right-hand side definition, how are you going to check all possible sequences, right? So it's good to show something is not continuous, right? To show it's not continuous, you just need to pick one sequence going to A where, where this doesn't hold, right? So the sequence definition is more useful to show something is not continuous. So, but normally to show something is continuous, you want to use the the left-hand side. So left-hand side, let me just rewrite. Limit x goes to A. Okay, so we're gonna move. So hopefully you all know what limit is. So before we had a notion of sequence, right? It means no matter how large we get closer. So here is something similar. What we want to say, as x gets close to A, f of x gets close to f of A, right? That's pretty much what you want to say. And here, the close is not a mathematical word. You need to express, because your definition of close could be far for me, right? So, maybe someone's definition of close is like different from another person's definition of close. So we need a universal way of defining what close means. So x getting close to A, it will be the parameter will be given by delta, and f of x getting close to f of A, we have a parameter epsilon. So the definition is given by for all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus A is less than delta, f of x minus f of A is less than epsilon. So is everyone clear on this, right? So let me just draw the picture to sort of show you what we mean. So how am I gonna do this? Let me think. Yeah. Let's say f looks like this. Yeah. So not very intuitive, but let's say A is here, f of A is here. Yeah. Oh, actually, that's pretty bad. Where is it? Maybe a little lower. So something like this. Yeah. So how we're gonna define close is we're gonna say, okay, no matter what ball you choose around f of A, this is called the epsilon ball, right? So f of A plus epsilon. That's pretty much what this means, right? These are all points, within epsilon of f of A. I could find a delta ball here, A plus delta, A minus, such that the image of every point in here lies in this range. Right, and then where's f of A? F of A is like it's like this point right here, right? But like basically, yeah. So for any epsilon ball you choose, I could find a delta ball such that everything inside my delta ball maps to somewhere here in this little strip. And that's what we mean by close, right? Because you think of epsilon as a really small number, right? So, okay, is everyone clear on this? Or at least like, the idea? Okay. So let's do some examples. So let's show limit x goes to 1, x squared. What is this? Is 1. So basically show x squared continuous at a equals 1, right? So let's write out the definition, right? So it means for all epsilon bigger than 0, there exists delta bigger than 0, such that what? If x minus a is less than delta, so my a is 1, right? Let's go back up. F of x minus f of a is x is f of 1, right? Which is 1. And f of x is x squared. So x squared minus 1 is less than epsilon. So is everyone clear on what we're doing? Then there's a then right here. Great. So again, so we have to show this holds for all epsilon bigger than 0. So let's let epsilon be bigger than 0. Be arbitrary. I need to find a delta, right? So let's try do scratch work, right? Let's try bounding, let's try to figure out what delta is, yeah? So I need to somehow relate x squared minus 1 to x minus 1, right? Because delta lets me control x minus 1, right? So how am I going to relate x squared minus 1 to x minus 1? Any ideas? Yeah, exactly. So let's split this to x minus 1, x plus 1. So now I can make this small, as small as I want, because I could choose my delta. So to make the whole thing small, I just need to make this small. Now, how do I do that? So one way to do it, I mean, there's many ways, but like one way to do it that I do is I just change where it's centered. So this is just times x minus 1 plus 2. Yeah. And then triangle inequality to make right. And then this is x minus 1 squared plus 2. So I can make x minus 1 small, so I can make x minus 1 squared small. And I can make x minus 1 small, so I can make x minus 1 times 2 small. Yeah? So ideally, we're done. Yeah, because, I mean, I could choose delta so that like this is smaller than epsilon. But let's work it out. But is everyone clear on the idea? Right? You always want, you have control of delta, right? Someone hands you an epsilon, they give you some epsilon ball, you have to choose a delta. So you always want to relate this thing to this thing somehow. Okay, everyone clear? Great. So let's do it. So the way I think of it is, I need to choose delta as some epsilon thing, right? So the nice thing is squares behave differently when you go from 0 to 1 and then 1 to infinity. So let me just do it 2 cases. Epsilon is bigger than 0. So, but it's less than or equal to 1. In which case, what do I know about x minus 1 squared? Like, I mean, what do I know about epsilon squared? How does epsilon squared compare to epsilon? Yeah, it's smaller, right? If you just think of a half squared as a fourth. So, I mean, you just guess a number, but really, I mean, hopefully you can see it. Like, let delta be, I'm going to guess epsilon over 4 should work. So, if x minus 1 is less than epsilon over 4, then x squared minus 1, we did all the calculation, right? X squared minus 1, if we go all the way to the bottom, is smaller than or equal to x minus 1 squared plus 2x minus 1. But then x minus 1 is less than epsilon over 4. So this is less than epsilon over 4 squared plus 2 times epsilon over 4. Hopefully I got this right. So epsilon squared over 16 plus epsilon over 2. Now, from what we said right here, right? Epsilon squared is smaller than epsilon, right? So this is smaller than epsilon over 16 plus, and this is clearly smaller than epsilon, right? Because this is what? 8, 9 epsilon over 16, which is less than epsilon. So you're done, yeah? So that's for the first case. I mean, of course, you didn't need to choose epsilon over 4. You mean, as long as you get something less than epsilon, you're good, right? And so it'll work for epsilon over 8, or like whatever number, as long as the numbers work out. So case 2, epsilon is bigger than 1. Then what can you tell me about the relation now? How does epsilon square compare with epsilon? Yeah, square is bigger. Yeah. So here I get this. So obviously we want to take square root now because we want to do it the other way. So I think this should work. So let delta be square root of epsilon over 4. Let me just try this. Yeah. So then for x minus 1 less than delta, which is equal to this thing, we have from the scratch work, x squared minus 1 is smaller than or equal to, you know, x minus 1 squared plus 2, right? And again, this is less than root epsilon over 4 squared plus 2 root epsilon over 4. So again, this is epsilon over, well, sorry, yeah, never mind. Epsilon over 16, then plus root epsilon over 2. So again, if this is true, then, you know, this is certainly true, right? Epsilon bigger than root epsilon. Yeah, like 2 is bigger than square root 2. Yeah. So this is smaller than epsilon over 16 plus epsilon over 2. And then again, you get 9 epsilon over 16, which is less than epsilon. And then you're done. Yeah. So you've proven x squared is continuous at 1. Is everyone clear on this? Hopefully. So they make it very complicated, but basically all you're doing is doing a lot of bounds. So yeah, I'll sort of go over like these proof-based ones next time, but I really just want to show you that let's see. So in general, most, how do I say it? Most functions, you know, are continuous in its domain. Yeah. So let me just say word of advice. Most functions functions continuous in its domain. So like even though 1 over x is not continuous at 0, I mean 0 is not in the domain of 1 over x, right? I mean the domain of 1 over x is 0 to infinity, and it's certainly continuous there. Yeah. So and then let me just say for the sequence definition. Yeah. So also hopefully you also learned that in one dimension, continuous functions are those you can draw without lifting your hand off the paper, right? Yeah. So if you look at here, right, this thing's discontinuous because when I put open circle and I put closed circle, I had to lift my pencil, right? As opposed to like x squared, where I could just draw continuously. Yeah. So next time I'll go over like more harder problems, but for now I said please practice epsilon delta proofs. Yeah, those would be crucial. I guarantee you that will be on the final. So yeah, practice epsilon delta proofs and how it works. And I'll end section early today. So great. Unless you have like homework questions, I'll stay for that.